Hello and welcome to this third video in our lecture on hash-based cryptographic primitives. In this and subsequent videos, we're going to focus on the SHA-2 algorithm. So this is one of a family of hashing algorithms that we've discussed before. I'm not going to go through the history again. I just want to highlight that around 2005, a team of researchers found a collision for SHA-1 in about 2 to the 69 operations. And notice this is much less than the 2 to the 80 security advertised by SHA-1, given that it has a length of 160 bits. So this was a little worrisome, so the NIST decided to encourage everybody to switch to SHA-2, and hopefully this would have happened by 2010. Now, even though right now there's a new version called SHA-3, let's just focus on the second version right now, but they're all pretty similar in terms of the algorithms. They're all based on modular arithmetic, and they use similar logical bitwise operations. So I think, once you've understood one of them, you're pretty well on your way to understanding the other ones. So the particular version of SHA-2 is the SHA-512. Now, remember that there are three versions based on the length of the message digest that they output in bits. So this algorithm takes a message whose length is up to 2 to the 128 bits, which is pretty big, and the output, that is the message digest, is 112 bits of a fixed length, as it should be. And remember that this is a block algorithm that processes the input in blocks of 1024 bits. So the overview of the algorithm here takes up 5 steps. So we're going to start this algorithm with a message to be hashed. And let's say this message has a length L in bits, and L has to be less than 2 to the 128. So remember that we're going to break down this message into blocks of 1024, so we may need some padding for this message to be of the right length. So step number 1 is to append padding bits with the following formats. Always going to be a single one and then a number of zeros needed to get to the appropriate length. And let's say the number of padding bits is P. How do you decide how many bits P you add? Well, the constraint is as follows. We want to make sure that the total length L plus P is equal to 896 modulo 1024. So you might wonder why we want something equal to 896 instead of 0 modulo 1224, since we're going to break up this message into blocks of this size. That's going to be clear in a minute, but let me point out right away that 896 plus 128 is equal to 1024. Okay, so step number 1 here is to add some padding bits. And notice that the padding is required. So even if L without P is already equal to 896 modulo 1024, you have to add at least 1 bit of padding. So I want you to think about the possible range of values for P. It's going to have to be at least P, and then I want you to think about what's the maximum possible value for P to make sure this constraint holds. All right, step number 1 is complete. Step number 2 is to add yet another field at the end of this, and this is going to be the length field. It will contain exactly 128 bits, and so this is the reason why we subtracted 128 from 1024 here, because we wanted to leave some space for this field. And what this field is going to contain is the binary representation of the value L. So this is called the length field because it encodes in binary the length of the original message before we added the padding. Okay, so that was step number 2. And notice at the end of this stage, we have a message whose length is equal to 0 modulo 1024. So what that means is we're actually ready to proceed with the hashing process. Let me skip step 3 for now and talk about step 4. So in step 4, we're going to take this new message, modified as we just described, and we're going to break it up into blocks M1, M2, etc., etc., up to n blocks, and each block is exactly 1024 bits because that's a requirement of this algorithm. And we're going to use a hash function that we're going to call f for now. And the hash function is going to take the first block as well as another value, which we're just going to call an initialization vector like we did before. And the output of this hashing function will be a 512-bit message digest, but it's only going to be a message digest for the first block. So what we're going to do is we're going to run the f function again, but this time with the second block, and the second input will be the output of the previous hashing step. I'm skipping some details here, but we'll get back to those later. So you see what happens is we're going to hash every block one after the other using the same hashing function. And notice that the output of one hashing function is fed as input to the next one. So that's step number 4. And then step number 5 is the final message digest of the final execution of f would be the message digest for the original message. Okay, so you might wonder, how does f works? Well, f contains 80 rounds, as we mentioned before, of basically the same set of operations, namely some um, bitwise shift operations and other logical operations. And in particular, this function is going to be using a buffer called h. And so at step 3 here, we need to initialize the buffer before we start the first hashing call. So that's a big picture of the SHA-512 algorithm, which is also depicted on the following slide. So I think most of it I've already discussed. Original message followed by non-optional padding, followed by non-optional field L. Break down the message into blocks of 1024 bits. Run the same hashing function on every block. And the only complication here is that it's not just the output of f that's fed to the input of the next invocation of f, but rather it's the addition. This is the addition modulo 2 to the 64 of this output with the actual input. So the input and the output are added together before they are fed as input to the next one, and so on and so forth. So this concludes our overview of the SHA-112 algorithm, and in the next video we're going to dive into the f function itself.